The rainforest does not announce danger with claws or teeth. Sometimes it uses color. At ground level, beneath a lattice of dripping leaves and filtered green light, the poison dart frog sits in plain view, unhidden, unhurried, its skin painted in colors that feel almost artificial against the wrought brown floor of the forest. Electric blues, lacquered yellows, polished reds, combinations so clean and bright they look decorative rather than defensive. To the untrained eye, this is a harmless detail in a vast ecosystem, a small ornament in the undergrowth. To the forest, it is a warning sign rendered in flesh. Aposematic coloration is not subtle by design. It evolved for predators that learn quickly or die quickly, for birds and reptiles whose nervous systems associate color with consequence. In the Amazon, visibility is expensive. Anything that can afford to be seen usually has already solved the problem of survival. The poison dart frog advertises itself because hiding would be inefficient. It does not run, it does not lunge, it does not posture. Its survival strategy is simple and brutally honest. Touch me, and your body will regret it. The irony is that this message, perfectly legible to predators shaped by millions of years of selective pressure, is routinely misread by humans whose instincts have been rewired by culture, screens, and the false safety of beauty. The frog's toxicity is not an innate magic trick. It is an ecological inheritance. Poison dart frogs do not manufacture their poisons from scratch. They borrow them. Their alkaloid toxins are acquired through diet, primarily ants, mites, beetles, and other small arthropods that themselves sequester defensive chemicals from plants and fungi. Over evolutionary time, the frogs developed the ability to absorb, modify, and store these compounds in specialized skin glands. The result is a living chemical vault, its contents shaped by geography and food web structure. A frog raised in captivity, fed a sterile diet, is often harmless. The same species in the wild can be lethally potent. This variability is not a footnote, it is the point. The poison dart frog is not a static object, but a moving intersection of rainforest chemistry, trophic relationships, and evolutionary trade-offs. In the wild, those toxins sit just beneath the surface, dissolved in a thin layer of moisture that coats the frog's skin. This moisture is not incidental. Amphibians breathe and hydrate through their skin, which must remain permeable to gases and water. That permeability is a vulnerability, one the frog has turned inside out. The same openness that allows oxygen to diffuse into its bloodstream allows toxins to diffuse outward. The skin is not a barrier, it is an interface. When a predator bites down, the chemical exchange is immediate. Pain, paralysis, nausea, cardiac disruption, depending on the compound and the dose. Predators that survive learn. Those that do not become part of the data set, evolution uses to refine the signal. Humans, however, rarely interact with poison dart frogs as predators. The danger emerges not from attack, but from contact layered onto habit. A wet hand reaches down to steady a fall. A finger brushes a leaf where a frog had been sitting moments before. Sweat runs down a temple and is wiped away without thought. A scratch on the knuckle, a cracked cuticle, a mosquito bite opened by absent-minded rubbing. None of these actions feel risky in isolation. Together, they form a pathway. The toxins do not need to be injected. They do not need teeth or barbs or intent. Alkaloids cross membranes. Mucous tissues, eyes, mouth, nose, are efficient entry points. Tiny breaks in the skin, invisible under forest grime, are enough. The frog does not chase you. It does not leap onto your hand. It sits. You move. The poisoning is self-administered, delivered by routine gestures that have worked safely everywhere else in your life. This is where the trap closes. Pretty equals safe is a rule that works well in supermarkets and poorly in rainforests. Bright colors in human culture are often associated with toys, fruit, decoration, and warning signs that are abstract rather than embodied. We are trained to interpret color symbolically, not chemically. The frog exploits this mismatch, not deliberately, but inevitably. Its colors evolved to speak to predators with different perceptual priorities, and humans stumble into the conversation without understanding the language. Camera crews know this better than tourists do. In professional fieldwork, poisoned dart frogs are treated with a kind of quiet respect that borders on indifference. No handling, no repositioning for a better shot, no touching the substrate without gloves if a frog has passed through. Even then, gloves are discarded, not reused. The discipline is not paranoia, it is pattern recognition. The most common accidents do not happen at the moment of contact. They happen minutes later, when the context has shifted and the body resumes its background maintenance routines, wiping sweat, adjusting glasses, rubbing tired eyes. The rainforest amplifies this risk. Heat increases perspiration. Humidity keeps skin damp. Fine grit works its way into pores and undernails, creating microabrasions. Insects leave behind punctures that barely register as pain. Every one of these factors increases permeability. The forest does not have to be hostile to be dangerous. It only has to be consistent. From the frog's perspective, none of this matters. It is not aggressive. It does not defend territory with force. It does not pursue threats. Its toxins exist to discourage contact, not to seek it. In evolutionary terms, the system works. Predators avoid the frogs. Populations persist. The bright colors remain honest signals because the cost of lying would be death. The only reason the system fails with humans is because we keep inserting ourselves into it without updating our assumptions. There is another layer to this story that is easy to miss. Poison dart frogs are not ecological villains. They are indicators. Their presence often signals intact microhabitats with healthy arthropod communities and stable moisture regimes. Many species are highly sensitive to habitat disturbance, disappearing quickly when forests are fragmented or leaf litter dries out. The same animals that can kill with a touch are among the first to vanish when the system begins to unravel. This paradox, lethal and fragile, should recalibrate how danger is understood in complex ecosystems. Even the toxins themselves are not uniform weapons. Different species carry different alkaloids with different physiological effects. Some interfere with sodium channels in nerve cells, preventing proper signal transmission. Others disrupt muscle contraction or cardiac rhythm. The famed batrachotoxins associated with certain species are among the most potent non-protein poisons known, capable of locking sodium channels open and causing fatal depolarization. Yet most encounters do not involve these extremes. More often, exposure results in burning sensations, numbness, nausea, or temporary neurological effects that serve as warnings rather than endings. The danger is real, but it is not theatrical. It unfolds quietly, internally, and often later. This delayed consequence is what makes the aftershock so insidious. By the time symptoms appear, the frog is gone, the moment forgotten, the chain of cause and effect broken in the mind. The forest seems to have struck from nowhere. In reality, nothing unexpected happened. The rules were followed precisely. Aposematic colors warned. Skin transferred chemicals. Human behavior bridged the gap. In the broader logic of the rainforest, this pattern repeats endlessly. Many hazards do not announce themselves as threats because they are not threats to the organisms they evolved alongside. They become dangerous only when unfamiliar bodies enter the system carrying assumptions that no longer apply. The poison dart frog is not an anomaly. It is a case study. It shows how survival strategies optimized for one set of interactions can become traps for outsiders who misread signals and underestimate processes that operate below the level of conscious awareness. Standing in the leaf litter, watching a frog vanish beneath a fallen branch, it becomes clear that the rainforest does not reward attention-seeking or punish curiosity. It punishes carelessness disguised as confidence. The frog's colors are not decoration. They are a boundary. Cross it with your hands, your habits, your reflexes, and the forest will let you poison yourself without lifting a finger. In the rainforest, speed is often mistaken for danger. Fast strikes, sudden lunges, explosive movement. These are the signals human brains are tuned to recognize as threats. Slow things, by contrast, feel manageable, predictable, safe. The tarantula lives inside that blind spot. It does not chase. It does not leap from across the forest floor. It moves with deliberate weight, each step measured, each pause extended just long enough to feel passive. This is not weakness. It is a strategy refined for a world where energy is precious and visibility is limited, and where survival often depends on being underestimated. On the forest floor, tarantulas are architecture as much as animals. Their burrows stabilize soil, their hunting regulates insect populations, and their presence signals intact microhabitats with consistent humidity and shelter. Many species spend daylight hours concealed beneath logs, inside abandoned rodent holes, or wedged into root tangles where darkness is permanent and airflow minimal. Their slow metabolism allows them to remain still for hours without cost, conserving energy while sensory hairs map the vibrations of the world above. To an inattentive human, these spaces feel empty. To the spider, they are home. The trap forms when human movement intersects with this stillness. A boot pulled on without inspection. A hand pushed beneath a log to clear debris. Gear lifted from the ground after a humid night. In the rainforest, darkness is not absence. It is occupancy. Tarantulas select shelters that buffer temperature and moisture, places where their bodies can maintain stable internal conditions without active regulation. Their large size amplifies heat loss and gain, so they rely on microclimates rather than speed to stay alive. When those microclimates overlap with human storage habits, conflict becomes inevitable. Contrary to popular myth, tarantulas are not aggressive predators of large animals. Their primary prey consists of insects, small arthropods, and occasionally vertebrates no larger than a mouse or frog. Their venom is designed to subdue these targets, not to incapacitate humans. But venom is only one layer of their defense, and it is rarely the first deployed. When threatened, a tarantula follows a predictable escalation sequence that many people fail to recognize because it unfolds slowly. The spider rises, lifting its front legs and rearing its body into a threat posture that exposes fangs not as weapons in motion, but as warnings held in place. This display increases apparent size and communicates readiness without committing to contact. If the threat persists, many New World tarantula species shift tactics. Using their hind legs, they flick clouds of urticating hairs from their abdomen into the air. These hairs are microscopic barbs designed to embed in soft tissue. They do not poison. They irritate intensely. The sensation is not immediate pain so much as invasive discomfort, a burning itch that escalates as the hairs lodge in skin, eyes, and mucous membranes. The evolutionary brilliance of this defense lies in its psychological effect. It creates an overwhelming urge to rub, scratch, and wipe, precisely the actions that drive the barbs deeper and spread them wider. The spider does not need to win a fight. It only needs to create chaos long enough to be left alone. This is where the aftershock begins. In the humid heat of the jungle, sweat is constant. Hands are already wet, pores open, skin softened. When urticating hairs contact exposed areas, especially the face or inner arms, the body reacts reflexively. Rubbing feels necessary. Blinking accelerates. The irritation intensifies. Swelling follows, not as a dramatic injury, but as a functional problem. Fingers stiffen. Grip strength drops. Fine motor control degrades. In isolation, this is an inconvenience. In the rainforest, it can become a liability. Jungle work depends on hands, steady placement on uneven ground, precise use of tools, controlled grip on ropes or machetes. Swollen fingers reduce feedback, increasing the risk of slips, cuts, and secondary injuries. The tarantula does not cause these outcomes directly. It initiates a cascade that human physiology completes. Bites, though rarer, occur when the escalation sequence is interrupted. A hand closes around the spider. A boot compresses its body. A cornered tarantula with no retreat option may bite as a last resort. The venom of most tarantulas produces localized pain, swelling, and muscle cramps rather than systemic toxicity. The bite is not designed to kill large animals, but it is far from trivial. Infection risk is elevated in tropical environments where bacteria thrive and wounds remain damp. Again, the danger lies less in the immediate injury than in the aftermath. What makes tarantulas particularly deceptive is the mismatch between appearance and effect. Their movements are slow. Their bodies are soft-edged, almost plush in texture. Their eyes lack the forward-facing intensity humans associate with predation. This aesthetic invites handling, curiosity, and complacency. Yet beneath the hair lies a sensory system tuned to vibrations and air currents, capable of detecting approaching threats long before contact occurs. The spider knows you are there. It is waiting to see what you do. From an ecological perspective, tarantulas are risk managers. Their longevity, some species live decades, demands strategies that minimize unnecessary injury. Every confrontation carries cost. Their defenses are layered to resolve threats at the lowest possible energy expenditure. Threat display costs little. Hair flicking costs more, but still avoids physical damage. Biting is the final option, used only when all other signals fail. Humans often experience only the later stages of this sequence because they fail to recognize the early ones. The forest amplifies this misunderstanding. Visual clutter makes it difficult to spot subtle movements. Low light obscures posture. The constant background noise of insects masks the sound of hairs being released. By the time the irritation registers, the spider is already retreating. leaving behind no obvious source. Like many rainforest hazards, the tarantula's impact is indirect and delayed, separated in time from the decision that caused it. There is a deeper irony here. Tarantulas are among the rainforest's quiet stabilizers. By preying on insects, they reduce pressure on vegetation. By occupying burrows, they aerate soil and create shelter for other organisms once they move on. Some species share their homes with symbiotic frogs that eat ants drawn to the spider's prey remains, while benefiting from the protection of the spider's presence. These relationships illustrate a system built on coexistence rather than conflict. Human injury disrupts that balance, not because the spider is dangerous, but because human behavior introduces unpredictability. Reaching blindly into dark spaces ignores the basic spatial logic of the forest. Objects left on the ground are claimed. Voids are occupied. The assumption that stillness equals safety collapses in an ecosystem where immobility is a form of camouflage and patience is a weapon. Even the panic response triggered by urticating hairs serves as a lesson in embodied ecology. The urge to rub is deeply ingrained, a reflex shaped in environments where irritation usually comes from dust or insects easily brushed away. In the rainforest, that reflex becomes maladaptive. Many defenses here are designed to exploit it. Stinging plants, biting ants, venomous caterpillars, and spiders all rely on secondary contact and self-inflicted escalation. The forest does not chase. It waits for you to finish the job. Watching a tarantula retreat into a burrow after a disturbance, it becomes clear that its goal was never harm. The encounter ends the moment space is restored. The spider resumes stillness, metabolism slowing, sensory hairs tuned once again to the tremors of passing insects. The human, meanwhile, carries the experience forward, itching skin, swollen hands, disrupted focus. The lesson lingers longer than the animal. Slow does not mean harmless. In the rainforest, it often means optimized. The tarantula's pace reflects confidence in defenses that do not require speed, strategies that turn human assumptions against themselves. The trap is not the spider. It is the belief that danger must announce itself with motion. Here, it waits in the dark gaps, beneath the gear, inside the boots, relying on the simple fact that you will reach before you look and rub before you think. In the rainforest, danger is often sorted incorrectly. Venom earns respect. Teeth earn distance. Anything without either is quietly downgraded, filed under manageable. The boa constrictor lives inside that misclassification. It lacks venom. Its bite is not spectacular. Its movement is slow enough to track with the eye. By human logic, this places it below the threshold of real threat. By biological reality, it places it in a category that injures through surprise, physics, and timing rather than chemistry. Boas do not need toxins to dominate their ecological niche. They rely on control, not incapacitation. Their bodies are built to turn contact into containment, and containment into imbalance. In forest environments where branches overlap, beams cross, and clutter accumulates, that strategy intersects with human movement in quiet, predictable ways. A boa resting in rafters or branches is rarely obvious. Its patterning mirrors bark, shadow, and lichen with unnerving accuracy. Irregular blotches break up outline. Muscle tone stays relaxed, reducing visible tension. Heat signatures blend into surrounding wood that has absorbed sun during the day. The snake does not coil tightly unless needed. It drapes. It conforms. It becomes structural. This is why the trap often begins with touch rather than sight. A hand reaches into roof beams to secure a tarp. Fingers wrap around what feels like a thick vine. A shoulder brushes something solid while stepping through dense growth. Camp clutter is shifted in low light. The moment of realization comes late. After contact, after weight transfer, after balance has already been compromised. Constriction in boas is not a continuous crushing force. It is a responsive system. The snake tightens when it senses expansion. When a body exhales, the chest narrows slightly, creating slack. The snake uses that moment to reposition coils. When the body inhales again, especially in panic, the chest expands against resistance and the coils tighten in response. The pressure does not increase arbitrarily. It increases in dialogue with breathing. This is where panic becomes an amplifier. Rapid, shallow breaths mean more frequent expansion attempts, each one triggering a tightening response. The person feels the squeeze worsen and instinctively breathes faster, feeding the loop. The boa does not need to think. Its nervous system is wired to respond to pressure changes automatically. The cycle reinforces itself. Importantly, many human encounters never reach full constriction. They do not need to. The danger arrives earlier during surprise, when balance is stolen. Imagine standing on uneven ground, one foot braced against a root, weight partially transferred. Your hand grips what you assume is a support. That support shifts. Muscles fire late. The center of gravity moves outside the base of support. The body falls, not because the snake attacks, but because the environment you trusted was alive. Falls near boas tend to be awkward rather than dramatic. A backward stumble off a ladder. A sideways collapse into gear. A slip from a branch when a vine flexes unexpectedly. Fractures happen this way. Wrist breaks. Rib impacts. Ankles twist. The snake may strike defensively at this point, not to hunt, but to create space. The bite, while not venomous, is deeply puncturing, designed to hold struggling prey. Infection risk in tropical environments is significant. Again, the boa is not the primary cause of injury. It is the trigger. Boas evolved this approach because it works across a wide prey spectrum. They hunt birds, mammals, and reptiles in environments where pursuit is inefficient. Their success depends on positioning and timing rather than speed. By anchoring themselves to branches or beams, they convert vertical space into leverage. A sudden grab or coil pulls prey off balance, letting gravity do part of the work. Thermoregulation plays a subtle role here. Boas often choose elevated resting spots that retain heat. Roof beams, sun-warmed branches, thick wooden structures. These locations double as ambush sites because prey passes through them regularly. Rodents run along beams. Birds roost nearby. Humans reach up. The rainforest is full of overlapping layers, and boas exploit all of them. They are as comfortable above ground as below it, transitioning between canopy, understory, and human structures with ease. This versatility is why they persist near camps and settlements without being seen. They do not seek humans. They simply use the same architecture. The misconception that non-venomous equals harmless ignores how injury actually happens in complex environments. Venom kills chemically. Constriction injures mechanically. Surprise injures kinetically. The boa sits at the intersection of the last two. Aftershock defines these encounters. Even if the snake disengages quickly, the body does not reset instantly. Adrenaline surges. Vision narrows. Fine motor control degrades. A person who has just stumbled from a beam or branch is more likely to fall again moments later. Cuts deepen. Secondary impacts occur. The initial surprise echoes forward. Ecologically, boas are stabilizers. They limit rodent populations that would otherwise explode around human structures. They reduce disease vectors indirectly by controlling prey species. Their presence often indicates intact habitat connectivity, where animals can move freely between forest and edge. Removing them increases imbalance elsewhere. Yet respect for that role should not be confused with underestimating the risk of contact. Boas do not need venom because they operate in environments where gravity, structure, and human assumptions do the work for them. They are not aggressive, but they are intolerant of being grabbed, stepped on, or treated as scenery. One of the most persistent myths is that constriction only becomes dangerous when the snake wraps fully around the torso. In reality, partial coils around limbs, shoulders, or necks can be enough to destabilize posture and breathing, especially in elevated or confined spaces. A loop around the forearm while standing on a ladder is sufficient to cause a fall. The snake does not need to complete the pattern. Watching a boa move deliberately through branches reveals how little effort is required to remain in control. The body flows, redistributing weight constantly. Every contact point is tested. The animal never commits all its mass at once. Humans, by contrast, commit fully and suddenly. We step, lean, grab, then trust the world to behave. The boa's trap exploits that trust. It does not rush. It does not strike first. It waits until it is mistaken for something else. In the rainforest, not venomous does not mean not dangerous. It means the danger arrives through mechanics rather than molecules, through surprise rather than poison, through a moment where balance is lost and the environment stops behaving the way you expected. The boa constrictor does not need to overpower you to hurt you. It only needs to be where you thought nothing alive could be, and let physics finish the encounter. The most dangerous predator in the forest is not the one that announces itself. It is the one that never enters your awareness at all. The puma lives almost entirely inside that absence. By the time most people consider the possibility of its presence, the conditions that made them vulnerable are already in place. The trap does not begin with a chase or a roar or a visible silhouette between trees. It begins earlier, in the quiet confidence that comes from feeling alone. Pumas are not built to dominate landscapes through intimidation. They are built to erase themselves. Every aspect of their biology favors invisibility over confrontation. Their coats fragment outlines rather than display pattern. Their footfalls are engineered for silence, padded to absorb impact and distribute weight across substrates that would betray heavier animals. Their eyes are tuned for low light, where contrast collapses and movement becomes suggestion rather than shape. They do not patrol openly. They position. Edge environments are their preferred geometry, where forest meets clearing, where trail meets brush, where river corridor opens briefly before closing again. These are not random choices. Edges concentrate movement. Prey follows predictable paths because resistance is lower, footing is clearer, and vegetation funnels travel into narrow bands. Humans do the same thing, often without realizing it. Trails feel safe because they are open. Clearings feel safe because they are visible. In reality, both reduce escape options while simplifying targeting. A puma does not need to see you clearly to understand you. It reads posture, pace, and rhythm. Lone movement stands out immediately against background noise. Groups create confusion. Individuals create signal. Even in dense vegetation, the cadence of a single set of footsteps resolves as a pattern. Stop-start motion, head-down posture, distracted scanning, these are not signs of strength. They are data points. Low visibility is not a limitation for a puma. It is an advantage. Where human vision degrades, at dusk, dawn, under heavy canopy, in broken light, the cat's sensory balance shifts in its favor. Ears rotate independently, mapping sound direction with precision. Whiskers detect subtle air displacement. Eyes pick up motion rather than detail. The animal does not need to see your face. It needs to know where you will be 2 seconds from now. The selection process is quiet and continuous. Pumas assess constantly, updating risk and reward without committing until certainty crosses a threshold. They are not impulsive hunters. Failed attacks are costly. Injury is unacceptable. As a result, most encounters never progress beyond evaluation. The human walks through the frame of possibility and out again, unaware that anything occurred at all. The trap tightens when humans supply the final variables themselves. Running is the most common mistake, not because it provokes pursuit in a cartoon sense, but because it clarifies intention. A sudden acceleration collapses ambiguity. It signals vulnerability, panic, and predictability all at once. Direction locks in. Path becomes obvious. The puma does not need to chase far. It only needs to intersect. Turning one's back compounds the problem. Humans evolved to face threats. Turning away feels wrong, which is why fear often drives people to do it quickly, without thought. In doing so, they remove visual tracking, surrendering information they might otherwise use to regulate distance and posture. For a predator adapted to rear-angle approaches, this is decisive. Separating from a group is another unforced error. Groups confuse targeting by creating overlapping movement, sound, and visual noise. When one person drops behind, moves ahead, or detours alone, even briefly, they reintroduce clarity. The forest does not interpret this as independence. It interprets it as isolation. Importantly, most injuries associated with puma encounters are not caused by the animal itself. They are caused by what fear does to human movement. Sprinting into dense vegetation shreds skin and destabilizes footing. Blind turns lead to falls on steep slopes or into rocky drainages. Ankles twist. Knees give out. The body becomes loud, erratic, and compromised. This is the aftershock phase, where the trap completes itself without contact. A person who has fallen, injured, and exhausted themselves in panic is now operating at reduced capacity in terrain that punishes imprecision. Even if the puma disengages, which it often does once conditions change, the damage is done. The environment becomes the hazard. Pumas understand this environment intimately. Their territories can span hundreds of square kilometers, mapped not in straight lines, but in routes of least resistance and maximum concealment. They know where slopes give way, where footing shifts, where vegetation thickens suddenly. They choose ambush points that offer multiple exit paths, ensuring they are never trapped themselves. Humans, reacting emotionally, move in exactly the opposite way, toward dead ends, steeper ground, and unstable surfaces. Thermoregulation plays a subtle but critical role here. Pumas avoid prolonged exertion in heat, favoring short bursts at optimal moments. This is why many encounters occur during cooler periods when human alertness is lower. At night or in twilight, when body temperature drops and attention wanes, the cat's advantage peaks. Humans misinterpret this calm as safety. Silence becomes reassurance rather than warning. Ecologically, pumas are keystone regulators. They shape prey behavior across entire landscapes, creating what ecologists call landscapes of fear. Deer, smaller mammals, and even mesopredators alter where and when they move based on puma presence. Over time, this redistributes grazing pressure, affects vegetation regeneration, and cascades through the ecosystem. Trails that feel open to humans may be avoided by prey precisely because they are too exposed. That absence should be read as signal, not invitation. The irony is that pumas are rarely interested in humans as prey. Their evaluation systems evolved for animals that move differently, smell differently, and behave differently. Most encounters end with mutual avoidance. The danger arises not because the puma attacks, but because humans misinterpret uncertainty as threat and respond with the worst possible movement patterns. Fear narrows perception. Peripheral awareness collapses. Breathing accelerates. Muscles tense unevenly. The body prepares for sprinting even when sprinting is disastrous. In forest terrain, speed without planning increases impact forces on joints and reduces reaction time to obstacles. The faster you move, the less time you have to adapt. The puma does not need to close distance. It only needs to wait until you injure yourself. In many recorded incidents, people report feeling watched before anything else happened. This sensation is not mystical. It is the nervous system reacting to subtle cues, unusual silence, altered bird behavior, changes in ambient sound that register below conscious thought. Ignoring that signal and continuing blindly often precedes panic-driven mistakes later. The forest speaks softly first. A puma that chooses to disengage does so silently. It melts back into cover, leaving no trace beyond disturbed leaves and a momentary absence of birdsong. The human, meanwhile, carries the encounter forward, heart racing, injuries throbbing, judgment impaired. The threat feels unresolved because it was never seen. This ambiguity fuels further poor decisions, extending the risk window long after the animal is gone. Understanding this dynamic reframes the trap. You never see the hunter, not because it is everywhere, but because it is selective. It waits for alignment, terrain, light, movement, and human behavior converging. Most of the time, that convergence never completes. When it does, it is often because the human finishes the sequence themselves. The rainforest does not reward fear. It rewards controlled movement, situational awareness, and restraint. Pumas exploit the opposite: haste, isolation, and predictability. They are not monsters lurking in shadows. They are indicators of intact systems where predators still regulate behavior through presence alone. Standing still, facing outward, maintaining group cohesion, and moving deliberately are not defensive postures in the human sense. They are ways of denying the final variables a puma requires to justify engagement. The cat is not offended by confidence. It is deterred by unpredictability. The trap is believing danger announces itself. In reality, the most consequential moments pass without spectacle. A decision to run, a step taken too fast, a turn made without looking. The puma does not need to strike. It lets fear drive you into worse terrain and watches the system resolve itself. You never see the hunter because seeing it would mean the system failed. By the time visibility arrives, the moment has already passed, either safely or not. The rainforest rarely injures you with a single decisive act. More often it overwhelms through accumulation, small forces applied repeatedly, too quickly to count, too subtly to stop. Leafcutter ants embody this principle with surgical efficiency. They are small enough to dismiss individually, familiar enough to feel harmless, and abundant enough to turn a moment of inattention into a cascading failure. Their danger does not come from venom or aggression, but from precision, speed and numbers, deployed along paths so old and well-worn they resemble infrastructure rather than animal behavior. At first glance, a leafcutter ant trail looks like a curiosity. A living ribbon of motion threading through the forest floor, ants flowing in opposite directions with near mechanical regularity. One stream carries freshly cut leaf fragments held aloft like green sails. The other returns empty-jawed, already accelerating toward the canopy. The movement is hypnotic, almost decorative. It invites observation, photography, even the impulse to kneel closer for a better look. This is where the trap closes, not with hostility, but with geometry. Leafcutter ants are not foragers in the casual sense. They are industrial harvesters, operating within a rigid logistical network. Each trail is a supply line connecting a specific patch of vegetation to a subterranean fungal farm that may span tens of square meters underground. The ants do not eat the leaves they cut. They use them as substrate to cultivate a specialized fungus, their true food source, in one of the most advanced examples of non-human agriculture on Earth. Every worker on the trail is part of a system optimized for speed, throughput, and redundancy. There is no pause for obstacles. Anything that disrupts the flow is treated as a problem to be solved immediately. The mandibles that carve clean arcs from leaves are not crude tools. They are hardened shears powered by muscle fibers that contract with astonishing speed for an animal of this size. Each bite is shallow, but it is fast and decisive, designed to slice rather than tear. Against plant tissue, this produces smooth, efficient cuts. Against human skin, it produces something else entirely. Dozens of neat, bleeding incisions delivered in rapid succession, often before the brain registers pain. The mistake humans make is assuming that harm requires intent or size. Leafcutter ants do not attack in the way predators do. They respond to pressure, obstruction, and vibration. When you kneel across a trail, rest a hand on the ground, or step unknowingly into a moving column, your body becomes a structural failure in their system. The ants nearest the disturbance bite reflexively, not as individuals making decisions, but as components responding to local stimulus. Each bite triggers more movement, more contact, more cuts. The sensation is delayed by seconds, not minutes. At first, there is only movement. Ants climbing, adjusting, redistributing around the obstruction. Then comes the first sting of pain, sharp but isolated. By the time you pull away, the damage is already done. Dozens of mandibles have opened the skin, each incision small enough to seem trivial on its own. Together, they form a pattern of bleeding that spreads quickly across exposed areas: ankles, wrists, knees, fingers. This is the trap chain in its purest form. Small workers cannot hurt you until they hurt you all at once. The cuts are not deep, but they bleed freely, especially in the heat. where capillaries are already dilated to shed excess warmth. Blood draws attention, not from the ants, but from your own nervous system. Pain demands focus. Focus narrows awareness. Awareness lost is the rainforest's favorite opening. In the humid understory, wounds do not dry quickly. Sweat flows immediately into the cuts, carrying salt that stings and grime that contaminates. Dirt embeds in the edges. Leaf fragments, fungal spores, and bacteria from the trail enter the skin. None of this is dramatic. There is no single moment of crisis. Instead, there is distraction, hands lifted to brush ants away, posture compromised, footing neglected. The injury does not end the task, it degrades it. Leafcutter ants evolved this efficiency not as a weapon against large animals, but as a byproduct of scale. Their colonies can number in the millions, each individual expendable, each action insignificant alone, but overwhelming in aggregate. This is swarm logic applied to herbivory, and it reshaped neotropical ecosystems long before humans arrived. Leafcutter colonies remove a measurable percentage of leaf biomass annually, influencing plant growth patterns, nutrient cycling, and even forest composition. Their trails aerate soil, redistribute organic matter, and create predictable corridors that other animals learn to exploit or avoid. Predators such as armadillos and anteaters specialize in breaking into leafcutter nests, trading short-term pain for caloric reward. Birds track trails to capture workers flushed by disturbance. Even plants respond, evolving chemical defenses or growth strategies to reduce cutting pressure. The ants are not background noise. They are architects of the forest's structure. Their ability to injure humans is incidental, but it is rooted in the same traits that make them ecologically dominant. The aftershock of a leafcutter encounter unfolds over days rather than minutes. The initial bleeding stops quickly, but the healing does not. In the tropics, minor wounds often remain inflamed longer than expected. Constant moisture prevents scabbing. Friction from movement reopens cuts. Sweat and heat sustain bacterial growth. What would be a forgettable scrape elsewhere becomes a persistent irritation, sometimes progressing to infection if not cleaned thoroughly and early. For field workers, this matters. Hands that ache and swell lose dexterity. Knees that sting alter gait. Small adjustments accumulate, changing how weight is distributed, how tools are handled, how attention is allocated. Fatigue sets in faster when the body is managing inflammation. Again, the ants do not escalate. The human system does. There is a subtle cruelty to this dynamic, though it is not intentional. Leafcutter ants punish the assumption that danger must be singular and visible. They operate at a scale that bypasses instinctive threat detection. You do not brace yourself for ants. You ignore them. You kneel where you should stand. You rest where you should hover. By the time pain arrives, the error is already past. Observing a trail uninterrupted reveals just how optimized the system is. Ants adjust their load size based on wind resistance. Traffic density shifts throughout the day to avoid thermal extremes. Larger workers patrol the edges, responding to vibrations with immediate defensive bites. Smaller workers maintain trail integrity, clearing debris and repairing damage. This division of labor creates a moving machine that does not stop for anything short of total destruction. Humans crossing that machine are treated as terrain, not as threats. Terrain that moves is destabilizing. Biting restores order by encouraging removal. From the ant's perspective, The interaction is successful if the obstruction withdraws. Pain is merely the mechanism. There is a lesson here that extends beyond ants. In the rainforest, size is not a reliable indicator of risk. Many of the most consequential injuries come from organisms too small to notice until they have already acted. Venomous caterpillars, biting flies, stinging plants, parasitic larvae, all rely on the same principle. Overwhelm through repetition, exploit reflex, let the environment do the rest. Leafcutter ants make this principle visible because their work is impossible to ignore once you learn to see it. Their trails are roads. Their nests are cities. Their fungus gardens are farms older than human agriculture by millions of years. They are not passive background life. They are a force, and forces do not need malice to cause harm. When you step back from a trail and watch it reform around the space you vacated, the ants closing ranks, leaves flowing again as if nothing happened, the imbalance becomes clear. The system absorbed the disruption and continued. The human carries the cost forward, stinging skin, compromised focus, slower healing. The rainforest did not attack. It simply operated according to rules that do not care about comfort or scale. Tiny workers can't hurt you is a belief that works only until numbers erase it. In the rainforest, injury often arrives not as a blow, but as 1,000 precise cuts delivered by organisms too small to respect, moving too fast to stop, inside a system that never pauses to see who you are. In the rainforest, solidity is often an illusion. What looks heavy, anchored, and dependable may already be empty inside, its strength quietly converted into air. Termites specialize in this transformation. They do not announce themselves with movement or sound. They do not bite, sting, or chase. They remove certainty instead. Their danger is not direct, and that is precisely why it works. A fallen log stretches across the forest floor, darkened by moisture, softened by moss, its bark rough and intact. To a human eye, it reads as stable terrain, a bench, a step, a handhold. Dead wood feels inert, finished, resolved. In temperate forests, that assumption often holds. In the tropics, it fails. Here, death is not an endpoint. It is a resource, and termites are among its most efficient consumers. Inside the log, unseen, a city has been operating for years. Galleries lace the interior like veins, their walls smoothed by constant traffic. Workers move soil and wood particles, soldiers stand guard at narrow choke points, and reproductive individuals remain sealed deep within chambers where humidity and temperature are precisely regulated. What remains of the wood is not a beam, but a shell, structural skin stretched over absence. It holds its shape until it is asked to do work. The trap is sprung by contact, a foot placed for balance, a hand braced during a descent, a log stepped on while crossing a muddy incline. The bark flexes, then fails. There is no warning crack, no gradual sag. The collapse is sudden, total, and directional. The wood does not splinter outward, it caves inward, folding around the force applied to it. The body follows. The injury rarely comes from the termites themselves. It comes from what waits around them. A fall into thorn-laced understory plants. A slip toward a water edge where footing disappears into mud. A knee driven into hidden roots, rocks, or stinging insects flushed by the collapse. The termites set the stage. Gravity delivers the consequence. This is not incidental to how termites live. Their entire evolutionary strategy revolves around consuming structure while preserving surface continuity. Exposure is dangerous. Open galleries invite predators, desiccation, and microbial invasion. Termites solve this by working from the inside out, maintaining an external facade for as long as possible. The result is wood that looks solid long after it has lost all load-bearing capacity. In the Amazon and other tropical systems, termites are not marginal decomposers. They are primary engineers. Alongside fungi and bacteria, they process vast quantities of cellulose, unlocking nutrients bound in lignin-rich plant material. Without them, dead wood would accumulate faster than it could be recycled, choking nutrient flow and altering forest dynamics. Termites accelerate decay while controlling it, shaping the physical architecture of the forest floor in ways that ripple outward through the ecosystem. Their mounds and subterranean networks regulate temperature and moisture with remarkable precision. Internal climates are maintained within narrow tolerances despite external extremes, using ventilation shafts, porous walls, and strategic orientation to sun and wind. This thermoregulatory mastery allows termites to operate continuously, day and night, rain or drought. The work never stops. Every log you step on has been evaluated, processed, and hollowed according to a logic that has nothing to do with human safety. Predators understand this logic intuitively. Anteaters probe carefully, tearing open sections with claws designed to breach without collapse. Birds peck and listen, testing resonance before committing weight. Even larger mammals distribute pressure cautiously, shifting balance constantly. Humans, by contrast, commit fully and late. We trust surfaces. We lean. The forest punishes that trust selectively. Not every log collapses. Not every branch fails. This inconsistency is what makes the trap effective. If every piece of dead wood were unreliable, caution would be automatic. Instead, the forest offers just enough stability to encourage habit. You step on 10 solid logs before the 11th gives way. The lesson arrives late. When collapse happens, it often coincides with other risks. Termite-softened wood tends to accumulate near watercourses where moisture supports decay. A fall here can mean sliding toward blackwater edges where visibility drops to zero. Insects disturbed by the impact, ants, wasps, beetles, pour out in defensive response. Thorns embedded in the understory, invisible from above, catch exposed skin. The termites are gone by the time the injury registers, their role finished the moment structure failed. The aftershock is psychological as much as physical. Falls erode confidence. Movement becomes hesitant. Decision-making slows as the body recalibrates its sense of stability. In dense terrain, this hesitation can be costly. Routes that rely on momentum, crossing slick roots, stepping between stones, navigating slopes, become harder when trust in footing is broken. Fatigue increases. Errors compound. Ecologically, this fragility is not a flaw. It is a feature of rapid nutrient cycling. In tropical forests, productivity depends on speed. Organic material must be broken down quickly to prevent nutrients from being locked away. Termites, by consuming wood internally, maximize surface area for microbial action while keeping material in place long enough to influence soil structure. When collapse finally occurs, it deposits partially processed matter directly into the forest floor, where fungi, bacteria, and plant roots can access it immediately. This creates a landscape in constant flux. Trails shift. Supports disappear. New hazards emerge where none existed days before. Animals adapted to this environment move lightly, constantly testing, never committing weight without feedback. Humans arrive with assumptions forged elsewhere, where dead wood rots slowly, where collapse announces itself with sound, where structure persists long enough to be trusted. There is a quiet irony in the termite's role. These insects are often framed as destroyers, yet they are builders at every meaningful scale. Their mounds alter drainage patterns. Their tunnels aerate soil. Their processing of wood fuels plant growth that stabilizes slopes and anchors riverbanks. The collapse they cause is not random destruction, but timed release. The forest depends on it. Human injury enters this system as an unintended side effect. When a person falls because a log failed, the termites did not act against them. They acted long before, following a blueprint refined over millions of years. The fall is the human moment of realization that the blueprint exists at all. Seen through this lens, dead wood becomes one of the rainforest's most deceptive features. It looks like rest. It offers the promise of support in a landscape that rarely provides it. But in a place where nothing is allowed to remain unused, death is temporary, and stability is negotiated moment by moment. Experienced field workers learn to read subtle signs. The sound of wood underfoot, dull rather than sharp. The way bark flakes when pressed. The presence of fine soil spilling from cracks. Even then, certainty is impossible. The safest assumption is that anything not alive is already being eaten. The termite's trap is not about fragility. It is about timing. The log was solid once. It will be soil soon. The moment you choose to trust it happens to fall in between. The injury that follows feels like bad luck, but it is not random. It is the predictable outcome of intersecting with a process that does not slow down to accommodate bodies unfamiliar with its rhythm. In the rainforest, the most dangerous failures are structural, not aggressive. They do not lunge or strike. They give way. The termites never touch you. They simply remove what you thought was there and let the forest do the rest. Along the rainforest's rivers, danger often wears the mask of spectacle. The water moves quietly, banks curve gently, and life concentrates along these edges because resources do the same. Light breaks through the canopy here. Insects gather. Fish rise. The riverbank feels open compared to the press of the forest behind it. When a basilisk lizard explodes from cover and sprints across the water's surface, it reinforces a seductive illusion that this edge is forgiving, that speed and confidence are enough to cross it safely. The basilisk's run looks like defiance of physics. For a few heartbeats, its feet slap the surface and do not sink. Ripples radiate outward, droplets scatter, and the animal appears to skim forward as if the river itself has turned solid. To a human observer, the message feels obvious. If something can run here, this place must be safe. That interpretation is wrong, and the cost of believing it is rarely paid immediately. What the basilisk performs is not a traversal, but an escape. Its body is light, its sprint explosive, its movement calibrated for panic rather than endurance. Enlarged hind feet with lateral toe fringes increase surface area just long enough to generate upward force during each strike. The feet slap down at extreme speed, trapping pockets of air beneath them and pushing water downward before gravity can take over. The lizard stays upright, not because the water supports it, but because it leaves each point of contact before collapse occurs. This mechanism only works under very specific conditions. The distance is short. The water surface must be relatively calm. The animal must accelerate instantly and maintain cadence without interruption. The basilisk cannot slow down, hesitate, or change direction mid-run. When the burst ends, it does not continue across the river. It dives, swims, or scrambles onto the nearest structure. The feat is not about crossing safely, it is about buying seconds. Evolution shaped this behavior in response to predators that hunt by ambush along riverbanks. Birds, snakes, and larger reptiles wait at the edge where prey congregates. For a small lizard, retreating into the forest can be just as dangerous as staying put. The water offers an escape route that confuses pursuit, breaks sightlines, and forces predators to switch modes, from lunging to swimming, often too late. The basilisk's run is not confidence. It is desperation refined into efficiency. Humans misread this because we see outcome without context. We notice the successful sprint, not the failed attempts that end in splashes, near misses, or underwater escapes invisible from above. We interpret the bank as stable because an animal used it as a launch pad. We assume the surface was supportive because something moved across it. In reality, the riverbank is one of the most mechanically unstable places in the rainforest. The soil here is saturated, compacted unevenly by fluctuating water levels. Roots lace through mud, creating hidden steps and slick ramps that shift under pressure. Algae coat exposed surfaces, turning gentle slopes into frictionless slides. Leaf litter collects and decomposes into a thin, lubricated layer that hides depth and texture. The bank looks walkable because vegetation holds it together, until weight is applied in the wrong way. This is where the trap forms. A basilisk runs. A human follows with eyes rather than feet. Curiosity or excitement overrides caution. A step is placed where the lizard launched, not understanding that the animal's mass, gait, and timing are entirely different. The foot meets mud that cannot support it. Balance shifts. The body compensates late. The fall happens not into open ground, but toward the water, where consequences multiply. The slip itself is rarely severe. A sudden loss of footing, a knee hitting mud, a hand thrown out instinctively to break the fall. The real damage begins in the aftermath. Wet clothes cling and pull. Skin meets abrasive roots or submerged debris. Impact stuns just long enough for disorientation to set in. Breathing accelerates. The heart rate spikes. Splashing follows. Along river edges, movement is information. Vibrations travel through water faster and farther than through air. Erratic motion, slipping, scrambling, splashing, broadcasts distress without intent. The basilisk's sprint avoids this. It is brief, directional, and ends cleanly. Human movement after a fall does the opposite. It is chaotic, prolonged, and loud. Even without naming specific predators, the pattern is clear. Riverbanks are not neutral zones. They are interfaces where multiple sensory systems overlap. Vision above water, vibration below, scent carried downstream. Many animals exploit these overlaps, waiting not for prey to arrive, but for conditions to shift in their favor. A human slipping into this space does not need to be hunted to be endangered. The environment itself becomes less forgiving the longer instability persists. The irony is that the basilisk avoids exactly this outcome. When it reaches the end of its sprint, it disappears decisively, either plunging fully underwater or clinging to emergent vegetation. It does not linger. It does not thrash. Its escape ends with concealment. Humans, by contrast, often try to recover in place, fighting the terrain rather than yielding to it. The bank punishes that resistance. From a physiological standpoint, the basilisk's performance is narrowly tuned. Its muscles are optimized for anaerobic bursts, not sustained effort. Its bones are light, trading durability for speed. Its thermoregulation favors basking near water, where evaporative cooling is effective, but this also ties it to zones of constant change. The animal lives at the margin because the margin gives it options. It can climb, dive, sprint, or freeze, depending on what the moment demands. Humans approach margins differently. We treat them as boundaries, places where one environment ends and another begins. In the rainforest, boundaries are gradients, not lines. The riverbank is not land transitioning to water. It is a dynamic mix of both, shifting hourly with rainfall, upstream activity, and sediment flow. Stability here is temporary by definition. Ecologically, basilisks occupy an important niche in these systems. They control insect populations, disperse seeds, and serve as prey for larger animals, linking aquatic and terrestrial food webs. Their presence indicates healthy riparian zones with intact vegetation and undisturbed banks. When basilisks vanish, it often signals erosion, pollution, or human alteration of waterways. The same instability that endangers humans is essential for maintaining these ecological processes. This duality, hazardous yet vital, is what makes the trap so effective. The riverbank looks inviting because life concentrates there. Movement is visible. Light penetrates. Compared to the dense forest interior, it feels navigable. The basilisk's sprint reinforces that feeling, transforming a narrow survival tactic into a perceived shortcut. But shortcuts do not exist here. The basilisk does not choose the water because it is safe. It chooses it because it is unpredictable. Predators struggle to commit fully to a medium that resists their primary hunting mode. Humans, lacking that evolutionary context, commit completely and too late. The aftershock of a slip near water extends beyond the immediate moment. Wet gear adds weight. Minor impacts stiffen muscles, reducing balance on subsequent steps. Confidence erodes, altering posture and movement patterns. Each of these changes increases the likelihood of further mistakes. The riverbank, once perceived as open and manageable, reveals itself as a cascade of compounding risks. Watching a basilisk from a distance, perched motionless on a branch above the water, its earlier sprint already forgotten, clarifies the misunderstanding. The animal is not advertising safety. It is demonstrating a last resort maneuver that works only because everything about its body and behavior is tuned to that narrow window of success. Remove any one element, speed, lightness, timing, and the run fails. For humans, the lesson is not about imitation. It is about interpretation. The rainforest does not show you what is safe. It shows you what is possible for those built to survive there. When a basilisk runs on water, it is not inviting pursuit. It is signaling that the edge you are standing on is unstable enough to justify risking everything for a few seconds of distance. The trap is believing that spectacle equals permission. The bank feels safe because something crossed it. In reality, it is safe only for an animal that knows exactly how briefly it can afford to touch it, and exactly when to disappear. Calm water is the rainforest's most convincing lie. It reflects the canopy cleanly, holds the sky without distortion, and moves so slowly that depth and distance seem obvious. To human perception, stillness suggests emptiness. If nothing breaks the surface, if no ripples radiate outward, the water reads as vacant space, an open corridor between banks, a place to wade, cross, or pause. In the Amazon, stillness is not absence. It is concealment perfected. Anacondas are built for this deception. Their bodies dissolve into the water not through camouflage alone, but through behavioral precision. They choose locations where visibility collapses naturally. Flooded grass, root tangles, submerged branches, leaf-choked shallows where tannins darken the water into opaque black. Here, the boundary between plant and animal disappears. The snake does not wait in open water. It waits where structure already breaks outlines, where currents slow just enough to carry scent and vibration without disturbing the surface. Unlike pursuit predators, anacondas do not need speed over distance. They need leverage at contact. Their hunting strategy is shaped by mass, buoyancy, and geometry rather than chase. The strike itself is brief, often less than a second, powered by a sudden release of stored muscular tension. The head emerges just long enough to secure purchase, teeth anchoring while the body flows forward. What follows is not violence in the cinematic sense. It is mechanical efficiency. The wrap is not about crushing immediately. It is about control. Anacondas coil to limit movement first, positioning loops around the chest or limbs in ways that convert struggling into advantage. In water, this leverage multiplies. Buoyancy supports the snake's mass while robbing the prey of stable footing. Each attempt to pull free feeds the system. Muscles contract, coils tighten incrementally, and circulation begins to change. Not catastrophically at first, but enough to alter physiology. This is where the human trap closes. The instinctive response to sudden restraint in water is thrashing, kicking, twisting, pulling hard against whatever holds you. On land, this can create space. In a constrictor's coils, it does the opposite. Every expansion of the chest, every surge of movement, gives the snake more information about where to tighten and how much force to apply. The anaconda does not need to overpower immediately. It only needs to let exhaustion arrive. Constriction is often misunderstood as suffocation. In reality, the primary mechanism is circulatory disruption. Tight coils impede venous return, preventing blood from flowing efficiently back to the heart. Pressure builds in capillaries, oxygen delivery drops, and the body's ability to compensate erodes quickly. Breath becomes shallow, not because the airway is blocked, but because the chest cannot expand fully against the pressure. Panic accelerates oxygen demand just as supply is being restricted. In water, this process accelerates further. The body works harder to stabilize itself. Limbs search for purchase that does not exist. Movements become less coordinated as oxygen debt grows. The snake senses these changes through touch, not sight. It adjusts continuously, tightening where resistance increases, relaxing where it does not need to hold. The system is responsive, not brute force. From the outside, the water remains calm. Ripples fade quickly. Vegetation closes over the disturbance. This is another layer of the trap. Without obvious surface chaos, the encounter feels contained, manageable, something that can be solved through effort. Humans are conditioned to believe that survival is proportional to exertion. In this case, Exertion shortens the window. Anacondas evolved this strategy in ecosystems where large prey is unpredictable and energy is costly. They feed infrequently, sometimes only a few times a year, and must ensure that each opportunity results in success. Their bodies reflect this economy. Dense muscle fibers generate immense force at close range. Lungs extend far down the body, allowing partial respiration even when coiled. Metabolism can slow dramatically after feeding, conserving resources during long digestion periods. Everything about the animal is tuned for patience, followed by certainty. They are also intimately tied to the hydrology of their environment. Seasonal flooding expands their hunting grounds, turning forest into shallow lakes threaded with submerged obstacles. As water rises, prey movement concentrates along edges and through channels where navigation is easiest. Anacondas position themselves at these bottlenecks, often remaining submerged for extended periods, nostrils and eyes just breaking the surface or hidden entirely beneath floating debris. Thermoregulation plays a role here as well. Water buffers temperature extremes, allowing the snake to maintain optimal muscle performance without basking visibly. In blackwater systems, dark coloration absorbs what little heat penetrates the surface, while depth offers retreat if temperatures shift. Calm water is not just hiding place, it is thermal refuge and sensory amplifier. The human error is assuming that visibility equals knowledge. Clear sight lines above water say nothing about what lies beneath. Still, water transmits vibration efficiently, especially low-frequency movements like footsteps, splashing, or sudden shifts in weight. These signals travel through the substrate and water column, advertising presence long before visual contact occurs. An anaconda does not need to see you to prepare. The wrong move is rarely entering the water. It is entering it without understanding how quickly conditions can change once contact is made. In many documented encounters, initial restraint was partial, a limb brushed, clothing snagged, a momentary hold that could have been disengaged with calm, deliberate movement. Panic converts partial contact into full engagement. Energy drains. Breath control collapses. The window narrows. The aftershock of such an encounter, even if escaped, lingers. Intense muscular exertion combined with restricted breathing leaves the body depleted. Lactic acid builds rapidly. Fine motor control deteriorates. Judgment slows. In the humid heat, recovery is not immediate. Weakness persists, increasing vulnerability to secondary hazards, uneven footing, dehydration, exposure. The snake may be gone, but the environment remains unchanged, and the body is no longer operating at full capacity. Ecologically, anacondas are regulators. They control populations of fish, birds, mammals, and reptiles, preventing overconcentration along waterways. Their kills redistribute nutrients, feeding scavengers and enriching aquatic systems. Even their presence shapes behavior. Animals alter crossing points, drinking times, and travel routes in response to anaconda activity, creating dynamic patterns that ripple outward through the ecosystem. Calm water is rarely neutral. It is often claimed. This is why the trap is so effective. Humans read stillness as permission. The rainforest reads it as preparation. Anacondas do not advertise themselves because they do not need to. Their success depends on being overlooked until leverage is established. The encounter is decided in moments measured not by drama, but by physics and physiology. Watching an anaconda glide just beneath the surface, barely disturbing floating leaves, reveals how little effort is required to remain hidden. The body moves as a continuous curve, distributing force evenly, never breaking the plane of water unless necessary. It is a lesson in restraint. The animal does not rush because rushing creates signals. It does not struggle because struggle wastes energy. For humans, survival near calm water depends on the opposite mindset. Slow movement, deliberate entry, constant awareness that the surface tells only part of the story. Most importantly, understanding that force is not always the solution. In encounters governed by leverage and exhaustion, restraint buys time where resistance spends it. Calm water is not empty water. It is occupied by systems that thrive on stillness, that turn quiet into cover and patience into advantage. The anaconda does not need chaos to win. It waits for you to create it yourself, then lets fatigue and breath loss finish what the coils began. In the canopy, emptiness is rarely empty. Branches that appear unoccupied often are, not because nothing is there, but because something has learned how to disappear without leaving. Tree boas perfected this art long before humans began reading forests as networks of handholds and footholds. Their danger does not come from pursuit or size, but from precision layered onto invisibility. The trap is not that the snake attacks. The trap is that the branch looks neutral until the moment it isn't. Tree boas do not stretch along branches the way many people imagine snakes should. They compress. Their bodies form compact coils draped over limbs like knots in the wood itself, curves echoing bark texture, color gradients aligning with lichen, moss and shadow. The head is rarely obvious. It is tucked into the coil, aligned with the branch's axis, eyes forward but unreflective, unless light hits at the exact angle. From below, above, or beside, the animal resolves as structure, not life. This camouflage is not passive. Tree boas actively choose perches that maximize visual confusion. Horizontal branches at eye level, vines crossing at irregular angles, limbs that sway slightly in the breeze, masking micro-movements. At night, when many species are most active, contrast collapses further. Colors that seem vivid in daylight, emerald greens, pale yellows, marbled whites, flatten into the same tonal range as surrounding foliage. Vision, already compromised by low light, fills in the blanks incorrectly. Humans are particularly vulnerable to this illusion because of how we move through vertical space. Climbing, descending, balancing, all require hand placement before weight transfer. We grab first, then commit. In the rainforest canopy or understory, this habit is reinforced by necessity. Roots, branches and vines become ladders. Each movement assumes that surfaces will behave consistently. The tree boa exploits that assumption. The strike range of a tree boa is longer than most people expect because the animal does not need to reposition before launching. Its coil is already loaded. Muscle tension is stored like a spring, aligned with the branch, oriented outward. When the strike comes, it is not a full-body lunge. It is a partial uncoiling combined with neck extension, just enough to reach beyond the visual boundary people mentally assign to safe distance. Hands that thought they were inches away find themselves within range. The bite itself is fast and shallow compared to venomous species, but it is decisive. Curved teeth hook and hold rather than slash, designed to secure prey long enough for the body to follow. In defensive encounters, the snake may strike and release, or strike and maintain brief contact. Either outcome produces the same immediate human response: startle. Startle is the true hazard. The sudden realization that a branch is alive triggers a full-body recoil. Muscles fire reflexively. Hands withdraw. Weight shifts backward or sideways without recalculation. In stable environments, this response dissipates harmlessly. In the rainforest canopy or on uneven ground, it propagates into a chain reaction. A foot slips on damp bark. A second hand reaches for a different hold, often blindly. The body twists mid-motion, center of gravity displaced, momentum carrying it where there is no support. The fall is rarely straight down. It is diagonal, scraping, colliding with secondary obstacles, protruding branches, hanging vines, gear slung across the chest. The snake may already be gone by the time impact occurs. Tree boas did not evolve to knock large animals from trees, but their presence intersects perfectly with the mechanics of human movement. Their hunting strategy depends on prey approaching within reach, often birds or mammals moving along branches at predictable heights. The snake does not chase. It waits, coiled in a location where movement funnels naturally. The strike is a correction, not an attack. A precise adjustment when the trajectory aligns. This precision is underwritten by sensory adaptations that humans underestimate. Tree boas read vibration through their coils, detecting minute changes in branch tension caused by approaching weight. They use vision selectively, not to scan constantly, but to confirm when a shape resolves into prey. Heat cues play a secondary role at close range, helping finalize timing. The result is a strike that feels sudden, not because it is fast, but because it was already decided before the human realized anything was wrong. The ecological role of tree boas makes this overlap unavoidable. They regulate arboreal prey populations, particularly rodents and birds that move through mid-canopy layers. By hunting along travel routes, they influence how other animals use space, altering movement patterns in subtle ways that cascade through the ecosystem. Branches favored by boas become avoided by prey, shifting pressure elsewhere. The forest reorganizes itself around these invisible anchors. Humans, entering this system temporarily, do not see those reorganizations. We see only empty branches and potential grips. We assume absence because nothing signals presence in ways we are trained to notice. The boa's success depends on exploiting that blind spot. Thermoregulation adds another layer to the illusion. Tree boas often select perches that retain heat after sunset, branches exposed to afternoon sun, structural elements of human shelters, beams that store warmth. These locations double as comfortable resting spots and effective ambush sites. A hand reaching up to adjust a tarp or check a beam is not just entering space. It is intersecting with a thermal gradient the snake already occupies. The aftershock of a tree boa encounter lingers because it destabilizes trust in the environment. Once a branch proves deceptive, every branch becomes suspect. Movement slows. Hesitation increases. Ironically, this can raise risk further as half-committed steps and tentative grips reduce balance and increase fatigue. The body becomes cautious in a landscape that demands decisiveness. Falls triggered by startle often cause injuries disproportionate to the initial event. Wrists fracture as hands reach back too late. Ankles twist on landing. Shoulders dislocate as bodies try to catch themselves against sloping surfaces. None of these injuries are inflicted by the snake. The boa initiates the sequence by existing where the human expected emptiness. Tree boas themselves rarely pursue further interaction. Once disturbed, They often retreat along branches, melting back into foliage within seconds. Their survival does not depend on confrontation. It depends on remaining unrecognized until contact is unavoidable. In that sense, the encounter is already over by the time the human reacts. There is a quiet lesson embedded here about perception and scale. The rainforest canopy is not an open workspace. It is a three-dimensional maze occupied at all levels by organisms that assume everything moving through it understands the rules. Tree boas assume prey will move predictably. Humans assume branches are inert. Both assumptions fail at the moment they intersect. Watching a tree boa at rest completely still reveals how little effort it takes to remain unseen. The body relaxes into the branch's curve. Breathing is slow, almost imperceptible. Even close inspection can miss it unless the eye knows exactly what patterns to question. The forest rewards this stillness with success. For humans, safety in these spaces depends not on speed or strength, but on deliberate awareness. Scanning before gripping. Testing before committing. Understanding that empty is often just a failure of perception. The branch is not empty. It is occupied by something that evolved to look exactly like what you expect it to be. The trap is believing that absence of movement equals absence of life. In the canopy, life waits motionless, aligned perfectly with the structures you rely on. The tree boa does not need to pursue you. It only needs to exist where you reach, and let surprise do the rest. Tiny things rarely trigger fear. In the human mind, danger scales with size, large teeth, heavy bodies, visible strength. The glass frog violates none of these expectations because it barely registers as an animal at all. It is small enough to miss, quiet enough to ignore, and so visually delicate that it feels closer to decoration than organism. Its translucent skin reveals organs like a diagram. Its limbs seem fragile, its presence fleeting. The trap begins with this aesthetic miscalculation, but the frog itself is never the threat. It is the invitation. Glass frogs live at the edge of water, not because they are drawn to danger, but because their entire reproductive strategy depends on it. Eggs are laid on leaves overhanging streams. Tadpoles drop directly into flowing water after hatching. Adults spend much of their lives perched on the undersides of broad leaves, suspended above currents that regulate humidity and temperature with exquisite precision. These are not casual habitats. They are some of the most mechanically unstable surfaces in the rainforest. Leaves near streams are never dry. Even during rainless nights, moisture condenses continuously from the air, collecting on smooth cuticles and forming invisible films that erase friction. Algae and biofilms grow quickly here, especially on surfaces that receive diffuse light and constant spray. To the eye, these leaves look no different from any other foliage. To the foot or hand, they behave like ice. The glass frog makes use of this slipperiness rather than suffering from it. Its toe pads are adapted to cling under conditions where human skin fails completely. Microscopic structures create adhesion through surface tension, allowing the frog to hold position on wet, smooth surfaces without effort. It can shift, hop, or freeze in place with equal ease. Its movements are precise and economical, never asking the leaf to support more force than it can provide. Humans do not move this way. When a glass frog is spotted, curiosity overrides caution. The animal is small, slow, seemingly defenseless. People lean closer. They step toward the stream edge for a better angle. They reach across leaves without testing stability. The frog moves lightly, disappearing along a leaf margin or dropping out of sight. The human follows, heavier, less coordinated, trusting surfaces that were never meant to carry them. This is the misdirection at the heart of the chapter. The frog draws attention away from the environment that defines the real risk. Chasing small animals shifts focus outward. Eyes track movement. Hands anticipate capture. Feet place themselves automatically. The ground beneath is no longer evaluated. Roots, slick with moisture, protrude at odd angles. Banks slope toward water under layers of decomposing leaf litter. Rocks are coated with slime, invisible until pressure is applied. The first slip is often minor. A foot slides an inch. Balance is corrected late, but successfully. This reinforces the illusion of control. The second slip compounds the first. Weight transfers abruptly. Muscles tense. Hands shoot out to stabilize against vegetation that tears or bends unexpectedly. Sharp roots scrape skin. Thorns hook clothing. The body drops lower, closer to the stream. Cuts appear almost immediately. Thin skin meets abrasive bark, jagged roots, or broken stems hardened by moisture. Blood flows freely in the heat, not dramatically, but persistently. Sweat mixes with it, carrying salt into open wounds. Pain registers, sharp enough to demand attention, but not enough to halt movement. This is the beginning of the spiral. Glass frogs never flee upward into stable terrain. They retreat toward water and cover, where footing degrades further. In following them, humans descend into zones of maximum instability. Stream banks erode continuously, reshaped by rainfall and current. What looks solid from above may be hollow beneath, undermined by flowing water. A step placed confidently collapses into mud, pulling the body forward. At this point, panic does not erupt, but focus narrows. The mind prioritizes immediate correction. Don't fall, don't lose the frog, don't get wet. Each of these goals competes for attention. The environment exploits this division. Slips become more frequent. Cuts deepen. Movements lose precision. The frog is long gone. The glass frog itself remains untouched, still clinging upside down to another leaf, organs glowing faintly through its skin as moonlight filters down. Its survival strategy has worked perfectly. It was never meant to fight or flee dramatically. It relies on invisibility and the instability of the space it occupies. Predators that pursue it too aggressively face the same risks humans do: missteps, falls, exposure. Many predators learn quickly. Humans often do not. Ecologically, glass frogs are indicators of intact riparian systems. They require clean, oxygenated streams and stable vegetation structures to reproduce successfully. Their presence signals that water quality is high and that leaf canopies over streams remain unbroken. In degraded habitats, they disappear early, long before larger animals show signs of decline. The same conditions that protect them, constant moisture, lush growth, complex terrain, are what make these zones hazardous to careless movement. Thermoregulation plays a subtle role here. Streamside environments buffer temperature extremes, creating microclimates that allow glass frogs to remain active without expending excess energy. Leaves over water stay cooler during the day and warmer at night. This stability benefits amphibians whose permeable skin makes them sensitive to temperature and humidity fluctuations. Humans seeking relief from heat are drawn to the same zones, mistaking comfort for safety. The pain spiral that follows minor injuries is not immediate catastrophe, but cumulative erosion. Cuts sting, encouraging hurried movement to escape discomfort. Hurrying increases slips. Slips create more cuts. Blood attracts biting insects whose presence adds irritation and distraction. Scratching follows. Focus fragments further. What began as a harmless chase after a tiny frog becomes a sequence of escalating compromises. Importantly, none of this requires dramatic failure. No deep wounds, no broken bones, just enough discomfort to degrade decision-making. In the rainforest, degraded decisions are often more dangerous than outright injury. They lead to wrong footing, missed cues, and delayed reactions to other hazards that operate on longer timescales. The glass frog's transparency is a metaphor as much as an adaptation. It reveals what is normally hidden: organs, veins, the inner workings of a vertebrate body. At the same time, it conceals the true danger of its environment by appearing harmless. Observers focus on what they can see clearly and ignore what remains opaque: the physics of wet leaves, the instability of banks, the cumulative effect of minor wounds. This pattern repeats across the rainforest. The most dangerous encounters are rarely with animals that attack directly. They are with conditions that invite pursuit, imitation, or confidence. The frog does not need to bite, sting, or poison. It only needs to exist in a place where following it requires abandoning careful movement. Watching a glass frog in stillness, clinging to the underside of a leaf, reveals how perfectly adapted it is to this edge world. Its heart beats visibly through its chest. Its limbs remain relaxed. It wastes no motion. It does not chase anything. It waits. When disturbed, it moves just enough to remain out of reach, trusting that the terrain will do the rest. For humans, the lesson is not about avoiding frogs. It is about understanding scale and context. Tiny does not mean harmless when it redirects attention away from the environment. The real hazard is not what you chase, but where the chase leads you. In the rainforest, pain rarely arrives as a single event. It arrives as a sequence: a slip, a cut, another slip, another cut, each one manageable. Together they form momentum. The glass frog disappears into the leaves, untouched. The human stands bleeding slightly, footing compromised, attention scattered, caught not by an animal, but by a trap built from misjudgment and moisture. The frog was never the danger. It was the distraction that let the rainforest apply its rules quietly, patiently, and without resistance.